our flagship product for Concurrent Real-Time Corporation. So what we'll do today is we'll talk about a brief introduction of Simulation Workbench, and we'll talk about why real-time simulation is needed. And then we'll talk about how our solution is superior to our competitors. And then we will proceed to talk about how easy it is to bring Adams model into Simulation Workbench and run it in real time. Okay, so what is Simulation Workbench? Simulation Workbench is nothing but a framework to simulate models in real time. So when I say real time, I'm talking about hard real time. So we rely on our own operating system called Red Hawk operating system, and this provides hard real time performance. And in fact, our operating system is being used by Navy, and it's integral part of the most reliable anti-ballistic missile system in the world, Aegis. So this is just a background. So we came about from aerospace defense industry, but now we are getting popular in automotive industry also. So my presentation today is going to be geared towards automotive industry, but rest assured we are very strong in aerospace industry as well. So Tony G talked about a specific example of a transmission and design there, and that was very informative. So when you design a vehicle, you go about designing different parts of the vehicle. Then you might have different teams putting in multiple years designing these components, and then you want to integrate that, and you can do that with Simulation Workbench. Okay, so Simulation Workbench is very critical and useful in many stages of model-based design paradigm. So model-based design paradigm, so we have different stages. We have the rapid prototyping, hardware in the loop simulation, and the final testing. We are useful in all those stages, and we will see some actual examples of each of those in the upcoming slides. So let's take an actual example. So in a FADEC development, or full authority digital engine control, so which is basically a ECU for the jet engine. So you can rely on software in the loop and hardware in the loop simulations. What you have here is you have this jet engine, which is basically a plant model, and you have the controller, which is a FADEC. That is again is a controller model in control system engineering parlance. So when you do the software in the loop simulation, what you do is you come. Okay, hold on. Okay, so when you develop the new algorithms for the controller, so it should be easy to test these new algorithms. For that, you can either choose to run this algorithm in Simulation Workbench in real time and talk to actual plant or actual jet engine, or you can talk to another jet engine model, basically the digital twin of your jet engine, and then evaluate the performance. So this is very useful to find out problems very early in the development cycle. That means you save tons of money on the cost of the development. And the next stage is the hardware in the loop simulation. Here, what you do is once you are happy with all the algorithms, you actually put the algorithm in the FADEC computer, and now you want to test how your FADEC computer performs under different conditions. For example, what happens if your jet engine has some problems? So you want to check whether your FADEC performs correctly or not. So this is very important for both reliability as well as the performance reasons. So what you do, you take the actual FADEC, you connect it to the model of the digital twin of your jet engine running in Simulation Workbench, and connect it to input-output cards. So these input-output cards again depends on the sensor signals that you need to transfer. So in case of aerospace, we support many different protocols. like airing 429, 1553, things like that. So all that stuff is in this. And here, once you have this hardware in the loop testing done, you can be sure that your FADEC is performing correctly. Okay, so this is the main reason why real-time is required here, because when you are connecting a real system like FADEC to a model, the model has to respond to the inputs and the signals from the FADEC in a deterministic, quick way. Otherwise, the FADEC computer will not perform correctly, and all your test is basically out of the window. You cannot use it anymore. So let's take another actual example. This we talked a little bit in the previous presentations, but in case of, say, vehicle development, it is very useful to have a feeling of how your final design behaves very early in the development cycle. Again, I keep stressing on that early on the development cycle, because any improvements you do early in the development cycle saves you a ton of money. Like Tony G was talking about, you can run these simulations in probably 1/10 of the time that it requires you to actually do that in the real world. So this is very important. So what you do in a man-in-the-loop kind of simulation, what do you do? So what you do is you create a digital twin of your model, you run it in real time under simulation workbench, and you provide the input to this model through some kind of maybe a steering wheel, maybe a pedal, things like that. You can connect it to the model and see how your model responds. So suppose, again, Tony G was talking about the leaf suspension. So what you want to do, suppose if you want to change the suspension a little bit, what you can do is you can go change the parameter in the Adams model, again, go over the real-time conversion and bring it back, and then run it in real-time in simulation workbench. And now the driver is going to feel the difference in the new suspension. This is again a very, it's an example driving simulator here. It is a mid-level driving simulator. We power driving simulators from, say, a simple desktop driving simulator all the way to big driving simulator that takes like maybe a football field sized building or something like that. Because this huge driving simulator, they are very useful in simulating more accurate G-forces on the driver. So, you know, you can move it linearly on the X and Y axis. You can kind of simulate the acceleration. It's useful on seeing the behavior of the vehicle. Okay, so the real-time simulation by us is, we have big advantages compared to our competitors. So one of the main advantage is using commercial off-the-shelf hardware. What does that mean? It means we do not use our own custom motherboards or custom processors or some custom components in our real-time simulation. So basically, we take commercially available motherboards, maybe say Supermicro, and then we take the commercially available, the greatest and latest processor from Intel. We put it there in the motherboard, and we make this. We make this thing work in real time. That's where our strength comes in. So, sorry about that. So, what does that mean? It means you do not have to. You can take advantage of the market immediately. So you can take advantage of the Moore's law. So when you have the fastest processor available, you can almost immediately take advantage of that. Meaning that, like, for example, so we have this Intel 6144 processor, which is basically a very fast processor with big cache, which is ideal for physical system simulation. That was available a couple of years ago, but Intel came up with an upgrade to that 6244 that came about in the last quarter, and we support it right away. So the processor is out in Q4 2019, and it is already available in our demo systems. We support it quickly. So this gives you a leg up compared to our competition, who are usually stuck to custom components. And also, Simulation Workbench is designed with multi-core in mind from ground up. That means that you can leverage many cores to run your task in real time. This is very important for running Adams model in real time. So when we cannot run models with high degrees of freedom in real time with a single threaded application, we can actually simply use more cores and bring that into a real-time capable model. So this is very important again. So using commercial off-the-shelf hardware also means you do not have to, like I said, rely on outdated equipment or outdated motherboard, outdated processors like our competitors do. So you can leverage the latest processor quickly. It also means that you can keep your own inventory for spare parts. You do not have to worry about your system going offline. You can just simply change the hardware component yourself. You do not have to really wait for us to give you the processor. So we also support a wide variety of I/O cards. So again, because of the commercial off-the-shelf nature, we support many I/O cards that's available in the market that's best for the job that our customers require. We also have our own I/O cards that are very advanced and relatively cheaper and better performance. We do have big variety of I/O cards available. So why is this useful? So I talked about that FADEC development and chassis development. So say in the chassis development, and you want to control a big hexapod from your model. So now you need to have a hardware interface for that to work. So you can control this big hexapod using maybe an Ethercat device or something like that. So how can your model talk to this device? You have to use this interface, Ethercat interface. And it is very easy to do in Simulation Workbench because the model is not aware of the hardware at all. So when you develop the Adams model, you just simply concentrate on getting your system accurate. It reflects your real system. That's all you need to worry about. You do not have to worry about any hardware whatsoever. There is no configuration of the hardware in the model itself. So when you bring in the model into Simulation Workbench, you click a button, the model will be controlling your hexapod automatically. There is no programming involved. There is no coding involved, nothing like that. Okay, we also have extensive support for third-party modeling packages and visualization packages. And of course, this means that when you have Adams model, you can actually make it talk to other modeling packages. Take, for example, you have your existing code in C or C++, and this is a validated code that you have been using for years, and you want to talk to that C++ code from Adams model. You want to integrate this in the bigger simulation. What do? You make a user model, you bring this C++ code into Simulation Workbench, and again, through the magic of RTDB or the real-time database, you can make the Adams model talk to your own C code without doing anything by yourself. It is all simple RTDB communication. Okay, let's move on to actually running Adams model under Simulation Workbench. So I think we already, both Ian and Tony talked about it a little bit, but this is just to give you a context. So you have this really high fidelity Adams model that has different components, and it has probably 2000 degrees of freedom or more complexity. Then when you want to run it in real time, before Adams real-time product, what you need to do is you have to rely on this manual conversion. And you need to manually convert this model into a real-time capable model. This means that there could be some error that you introduce. Maybe you validated your high fidelity Adams model, but in the conversion process, you make some mistake, then you are going to actually have a problem down the line. So what we do we have Adam's real-time product. So using that product, most of this process is automated. So there is still some manual input, and like Ian was talking about, they are moving towards more and more automation. But this is already a big step forward, where you have this from high fidelity Adams model, create a real-time capable model that is that can run in real time under simulation workbench. So once you have this real-time capable model running under simulation workbench, what you can do is you can now use it in different applications. You can use it in a man-in-the-loop simulation kind of environment. You can put it on a driving simulator, test the behavior of the vehicle, check it, or you can probably connect it to Dyno, like how the Tony G explained. So you can put it in a Dyno environment, or you can again talk to this Adams model from different models, and you can do an integration testing under simulation workbench. So I have a small video, and again, hopefully this goes well through the internet, but so it just shows how easy it is to bring Adams model into simulation workbench. Okay, so what I'm doing right now is I'm going to the Adams import panel. I'm navigating to a Adams model, which is in an FME format. And here, what I'm doing is optional. This is useful if you want to run your model in multi-rate. So I'm mapping some Adams parameters like thread affinity. So which CPU cores I can run an Adams model that I can control. So after that, I create Adams RTDB. And this is the magic portion, and this is basically a glue that allows Adams model talk to hardware or other models, everything. So all that portion is automatic there. So once I have that, I can create a test. So creating test, again, very simple. You just add this Adams model. That's it. You have the test available. And now, again, this is the optional portion where I'm specifying which code I want to use for the multi-core simulation. So I'm using cores 3 to 8. I have the initial conditions ready. Now I'm all set to do the real-time simulation. Again, simply clicking a button, the model is running in real time. You can see it's using different cores. And again, this is running under my old system, but newer systems we can even run faster on these models. So as you can see, it's barely 1 minute video, but the steps are pretty intuitive, and you have to basically do everything GUI based. You do not have to worry about actual coding, actually writing some C code. This is very important for people that are not very well versed with coding. They are very good at simulation, creating a nice model that reflects the reality, but they do not want to actually do the coding. So this is very important for them. Okay, so let's go to the next slide. So let's go to an actual case study that Tony G already covered extensively, but let me talk about it in a more from a hardware perspective. So first of all, to run this 105 degrees of freedom model in real time, you need a lot of horsepower. So what we have with simulation workbench is it's basically a compute engine that takes advantage of a lot of cores that can run your model in real time. We were able to run it in real time, and for that particular application, we needed to talk to a legacy real-time system. So initially, there needs to be some communication that has to go back and forth. We went with Ethernet initially. Once we had that Ethernet, we could do it very quickly. Again, this communication from simulation workbench to D spaces, again, you do not have to write any code. Click a button, Ethernet packets will start flowing, and that's how you get the data back and forth. We had that, but there was a problem because Ethernet, by definition, the normal Ethernet communication is not deterministic, slow. So they needed a tighter feedback between in the loop. So we suggested using reflective memory, which is very fast, very deterministic. So we were able to switch it, and again with a few clicks. So you do not have to do any coding. Just unmap your Ethernet mappings, and you map the reflective memory, and you are all set. Now you will be talking to the D space using reflective memory without any coding. And the other important part is you do not have to even recompile model or re-import Adams model, nothing like that. So similarly, once we have this model running in real time, we were able to test the performance using simple Logitech wheel. So we just basically connect the steering wheel input to the model and see how it responds. We could do it quickly. And if you want to change this to, say, better sensor wheel, again, it would be very easy to do. All you want to do is unmap the Logitech wheel, just map the sensor wheel, and you are all set to go. This slide, again, this video I took in the last MSc workshop in Japan. Basically, it shows Adams model running in real time under simulation workbench, and you are seeing the wireframe of basically the Adams model, and you can see the car is moving there, and we saw already some bunch of videos there. But in this case, this model was approximately 100 degrees of freedom complex. But an update to that is basically now we are able to run models that are almost twice as complex. So almost 170 or 175 degrees of freedom models, we are able to run it in real time under 1 millisecond sample time. So we are testing out newer processors with the newer processor and some other new technologies here that will probably even improve this further. So in one of Ian's presentation, one of the slides, he talked about engineer's dreamland, where you have this simulation speed real-time capable. At the same time, you are able to run 2000 degrees of freedom or more in real time. Hopefully, we'll get there sooner rather than later, using your products. Okay, what are the key takeaways from this presentation? So first thing is interoperability. So first of all, once you bring the Adams model into simulation workbench, you can make it talk to other models, and you can make it talk to other hardware very quickly, and it is very important for customers. And we also bring in a lot of computing power. So basically, I can proclaim that our real-time solution probably has the highest, highest power over there. So I can make that claim. Okay, I'm sorry about that. And the third point is hardware support. So again, like I said, it's very easy to get the Adams model talk to hardware without actually writing a driver, without actually knowing anything about the hardware. Everything is GUI based. So all you do is you click a button and you get the Adams model talk to the I/O. So this comes back to one of the questions earlier. How do you get the people that are very well versed with simulation interested in HIL and interested in the SIL, interested in MIL? This is how you do it. So you make it all very easy, GUI based. That way they create the model, they concentrate all their effort on creating a very accurate digital twin of your physical system.